Hello all. Okay, so I hope I have sorted out my video resolution issue. We'll see. Um, okay, so continuing on the problem of least squares, I now want to take a little time to go over one quite interesting way to approach least squares, which serves to address some of the problems we saw last time when I was doing the fitting of the Canada data. And if you'll remember, we ran into this issue of the matrix being badly conditioned. So that means it was close to being non-invertible. And these ill conditioning issues, as they are called, they can be attacked in a variety of ways. And one of the ways we have to address that problem is through what is called the QR factorization. And so in this lecture, and further examples that I'll do on paper and on the computer, I want to spend a little time talking about this factorization issue. Okay, so the first thing that I'm going to point out is that for those of you who do a bit more math later or applications of math, so for instance, people with an engineering twist, you will see many other factorizations, because factorizations for matrices, they're something that is very, very useful. And they come out in a variety of topics, mostly dealing with the computational aspects of things. So matrix factorizations typically allow you to carry out computations in a way that's more efficient or that alleviates some of the problems that you encounter if you do brute force computations. So as I pointed out, there's several types of factorizations, just to give you a name. So for example, one that is well known and that you might see in another context is the so-called LU factorization. There's also what we call canonical forms, which are sort of factorizations. But anyway, this is a sort of prevalent topic in matrix analysis, and it comes up in a variety of topics. But to set the stage for the one that we're going to look at, which is that QR factorization, we need to first go through a little bit more detail about what are called orthogonal matrices and orthogonal sets. And this is what is going to be used to make this factorization. So as I've done in the past, this video here, so these slides that I'm presenting here are mostly on the theoretical side, and then I'm going to do an exercise or two by hand, and I'll also show you how to do the same thing on a computer. And I think it's important to see a little bit of everything. So on that theory side, the reason why I'm emphasizing this, and I'll sort of answer some questions that I've had from some students, I'm not going to test your capacity to carry out the very complicated theoretic side, but I think it's important to get a sense of where things are coming from, and that's why we're spending a little time doing this. So, without further ado, let's look at orthogonal sets. So we've seen linear independence, so linear independent set. This is another set property that we can ask of vectors. It's what we call orthogonality. So we're taking a set v1 to vk of vectors. Each of these vectors is in Rn, so there might be more vectors than the dimension of the space. There might be fewer vectors, there might be the same number, but it doesn't really matter. Okay, so I take k to be any number, I take k such vectors, and they're all in Rn. And we're going to say that that set of vectors is an orthogonal set if whenever I take two indices I and j that are not equal to each other, the dot product of vector vi and vector vj is equal to 0. That means the vectors vi and vj are orthogonal in the sense of orthogonality as we've defined it in the past. Okay? And there is a very interesting property of orthogonal sets of vectors. It's that if I have an orthogonal set of vectors, and that furthermore, none of these vectors are the zero vector. Okay, so remember when I say zero vector, I really mean the vector with all zeros. I'm not talking about a vector with some zeros, I mean the vector with all zeros. So if I have an orthogonal set so that each pair of vectors in the set are, we often say pairwise in the orthogonal. Okay, so if I have an orthogonal set and all the vectors are non-zero, then that set is also linearly independent. Okay, and this is an implication. You can have a linearly independent set that is not an orthogonal set, but in this direction it works. Okay, if I have an orthogonal set and none of the vectors are zero, then I have linear independence of the vectors in the set. And the same way we saw when we were looking at the revisions of linear algebra from first year, where I sort of pointed out that probably some of you had not seen bases. So we're going back to bases, and I've explained sort of in passing what that means. Okay, it's a way to represent vectors in a subspace or in a space. So if I have a set of vectors that forms a basis of a given subspace W, and if that set is orthogonal, then we call that basis an orthogonal basis of the subspace. So the first thing I'm going to do is to show you how to prove theorem 2, because I think it touches on that notion of linear independence, which is really something that I hope you sort of understand in this course. Okay, so this is something, as soon as we talk about linear independence, I'm probably going to show you how to do things, because I really want you to get a sense of what it means to be linearly independent. Okay, so let's look at the proof of this theorem. So we want to prove the statement there in theorem 2 that if we have an orthogonal set and that all the vectors are in this orthogonal set are non-zero, then we have also a linearly independent set. So to start, I'm going to assume that I have an orthogonal set and that all the vectors are non-zero. Okay, and I'll remind you what we saw in the linear algebra review is that a set of vectors v1 to vk, that set is linearly independent. And just in passing, you can see I'm writing li because it comes up so often that I'm going to use this. So a set of vectors v1 to vk is linearly independent if the only way for the linear combination of all those vectors multiplied by scalars, okay, so c1 to ck are scalars, and I'm multiplying c1 by v1, and I'm adding all of that. So if the only way to get the zero vector when you're taking these linear combinations is for all the coefficients that you have to be zero. So let me assume that I'm taking some c1 to ck in numbers in R, okay, and that they are such that c1 v1 plus c2 v2 plus so on and so forth to ck vk, that this is the zero vector. Now we're going to use a little trick that that seems very simple when you think about it, but that is used very often. It's the fact that zero is very powerful if you want to think about it that way. So for any vector x in Rk, that should be Rn, by the way, never mind, I will correct the slides. But so for any vector x in Rn, if I mean, this one is true. So if I'm talking about Rk here, this is the correct notation, but I will fix this. Okay, so whenever I have a vector, any vector, if I take its dot product with a zero vector of the corresponding proper dimension, then I will get the number 0. Okay, so what I've written here, I'm going to exploit by saying, okay, I've got the 0 vector there on the right, so I can multiply this on the right by some vector. And just because why not, let me take one of the vectors of that orthogonal set that I'm considering. So I'm going to take some value, some vector vi in my orthogonal set. And I simply rewrite here this equation that I have and this equation. Okay, so I'm writing that 0, the number 0, note that it's it's not a bold-faced 0, the number 0 is equal to the dot product of the vector 0 with this vector that I chose, vi. But this number, this vector 0 here, I've assumed that I could get it by this formula here, okay? This is what I've assumed, so I'm supposing, yes, I've found C1 to Ck that are such that the sum of those vectors is 0. So I just replace my 0 by this other expression that I have for 0, okay? But now, then this is a dot product of a, so here I have a sum of vectors on the left, and I have another vector on the right, so I can expand, okay? And so this is what I'm doing here. I'm simply expanding with respect to the dot product. So I get C1 times V1 times Vi, with dot product Vi, plus so on and so forth, all the way to Ck dot times Vk. So Ck here is a scalar. I'm multiplying it by Vk, which is a vector, that I'm also in turn dot producting, let's say, with Vi. Now, because that set V1 to Vk is orthogonal, by definition, I know that whenever I take two vectors in this set, the only one that is not 0 when I take the dot product is when I take the semi-entry. So 2 by 2, all these vectors are orthogonal. That means that Vj times Vi, let's say, is equal to 0 whenever I is not equal to j. Okay, so in this expression here, whenever I have something like this and that k is not equal to I, or here that I is not equal to 1, all these terms, they disappear. So this means that this equation here, it reduces to the only one that is not disappearing is Vi dot Vi. Okay, so I get Ci times Vi dot Vi is equal to the number 0. And this is equivalent, if you recall, when we were doing the review of first year linear algebra, that Vi dot Vi is the square of the norm of Vi. So this is what I'm writing here. So this whole equation boils down to Ci times norm of Vi squared is equal to 0. But I have assumed that none of the Vi's are the 0 vector. Okay, so that means, if you recall the properties of norms, the norm of a vector is equal to 0 if and only if that vector itself is equal to 0. So that means that the norm of Vi is non-zero. So here I have a product of two numbers, okay, Ci times the norm of Vi squared, and that product is equal to 0. So I know that the only possibility, these are scalars, so the only possibility, since the norm of Vi squared is non-zero, means Ci must be 0. And this has to be true for all I. So I have the result, because the only way for this expression to be true is for all the VI's to be, all the CI's to be 0. Okay, so we have linear independence. And okay, I want to sort of again emphasize the links with linear independence, etc. So let me just give you the most simple example almost that we could think of. So let's think about the standard basis of R cubed, which we've already seen. So these are the vectors I, j, k, where I has 1, 0, 0, j has 0, 1, 0, and k has 0, 0, 1. And I'll remind you that what we've seen is if we were working in a higher dimensional space, we would write EI instead of IJK. Now, if I take any of these two vectors together, and even the three of them together, I have orthogonal sets. This is easy. I mean, if you take the dot product of this vector, for instance, I with j, you can see that what I end up doing is the product of 1 and 0 plus the product of, 0 and 1 plus the product of 0 and 0. I get 0. Okay, so this is going to work for any two and any of the three taken two at a time. So those standard basis vectors, they're non-zero. They all have a non-zero entry. So the set, by the theorem we saw before, the sets are linearly independent. And also, if we take ijk together, we get this a set of vectors that spans the entire space. And I know there has been some questions about the span. So let me just show you, because perhaps you don't remember or you haven't manipulated that very much, how you compute the span of these three vectors. So if I'm going to take the span of these three vectors, what I'm going to do is take all the linear combinations of I, j, and k. So that means I'm going to take three numbers, C1, C2, and C3, and sum C1 times I plus C2 times j plus C3 times k. And when I do this, well, I can expand the way that's written here. Okay, so this is C1 times I plus C2 times j plus C3 times k. When I'm taking this product, this is the product of a scalar times a vector. That means I'm multiplying every entry in the vector by C1. So that means this first vector is C1, 0, 0. This second vector is C0, C2, 0. And this third vector is 0, 0, C3. And then finally, when I add them, I add corresponding entries in the vector. And so what I get is this. And the span of I, j, and k is therefore this vector for any value of C1, C2, and C3. And when I make all these values change, what do I get? I get the entirety of R3. So the span of these three vectors is R3. So it's a basis of R3. And furthermore, the vectors are orthogonal, so this is an orthogonal basis of R3. And actually, we can go a bit further. It's what we call an orthonormal basis of R3. So if to what we defined before, we add the property, the requirement that the vectors be of norm 1, okay? So if I have an orthonormal set and that each vector in the orthonormal set has norm 1, then what I have in the orthogonal sets are, so very easy to get them mixed up. So if I have an orthogonal set and each vector has norm 1, then what I have is an orthonormal set. And the same way, a basis that's constituted of orthonormal vectors is an orthonormal basis. So in the previous case, this is an orthonormal basis of R3. okay? Because all of these vectors have norm 1 and they're orthogonal and they span the entire space, okay? Let me just point out that in a way, that means that if you want to determine whether a set of vectors is orthonormal, what you have to do is you can use this definition here. I mean, you could use a slightly revamped version of a definition, which would be that that set is orthonormal if I get, whenever I take the dot product of the two vectors, then I get 1 if the indices are the same and 0 any other time. Okay. So let's move on to the next topic. So we're sort of moving towards the QR decomposition. And so now we're going to look at matrices. And the same way as we've looked at matrices whose columns were linearly independent by saying I have a bunch of columns and each of these columns is linearly independent from the others. The same way as we did that, we are going to look at a matrix and the columns, and we look at what type of set these columns describe. So if I take a matrix Q, and it's not a square matrix, okay, it's an n by n matrix, we say that the columns of Q form an orthonormal set, if and only if, so that's a result, okay. Q transpose times Q is equal to identity. Okay, this comes directly from this remark that we made here. Okay, so if I'm taking a matrix, it has, so that matrix, it's in Mn, so it has m rows and n columns. So the columns, I'm looking at the n columns here, and I'm looking at them as vectors, okay? So each column in the matrix is a vector, and I'm looking at these vectors. And what I find is that one way to see whether this is satisfied is to compute Q transpose times Q and to check whether this is identity. So I'll remind you of one observation we had made in the past and that I've used again several times since, that if I have a non-square matrix, when I take Q transpose times Q or Q times Q transpose, I automatically get a square symmetric matrix. Okay. So here, saying that Q transpose times Q is identity is not shocking. And so what we want to do when we're doing this Q transpose times Q, we're just checking that all these dot products are actually 1 only on the main diagonal, which means when I equals j, and 0 outside of the main diagonal when I is not equal to j. Okay, so that's another way to see this, and I'm not going to prove this result. Now, a matrix, if it's square and it has the property that its columns form an orthonormal set, we call an orthogonal matrix. Okay, so if orthonormal, sorry. So we call orthogonal a matrix whose columns form an orthonormal set. Okay. So from the definition of a theorem you had just above, you see that, so if I have a square matrix, it's going to be orthogonal if and only if this is true. Okay, this was this property here. So qt times q equals identity. But when you write that a matrix A times another matrix B, their product is identity, and that the matrices are square, you're saying that one of the matrices is the inverse of the other. Remember, this is how we define the inverse of a matrix. We say that B is the inverse of A if A times B equals B times A equals identity. So when I write that Q is orthonormal if and only if QT times Q equals identity, what I what I can interpret this as saying is that Qt is actually the inverse of Q. Okay, and that's what is written here. And so that gives us the following theorem, which is a necessary and sufficient condition for orthogonality, which is that a matrix in a square matrix, okay, careful, this is for square matrices, a matrix Q in Mn is orthogonal if and only if its inverse is equal to its transpose. And that's the property that we're going to use most of the time to check that orthogonality of a matrix is satisfied or not. We're going to check that the matrix has the transpose as its inverse. Now, orthogonal matrices, I could speak about them for quite a while. They have a bunch of very interesting properties, but I'm not going to spend that much time on them. I'm going to show you some interesting properties nonetheless, because I think these are interesting things to consider. So first, we'll start with the following or equivalent type result. And they hint at a very important property of orthogonal matrices, which is that they are the representation of a linear transformation that has a specific property, which is called isometry. Okay, so let me show you this theorem. I mean, explain this theorem before I explain what this means. So if I have a square matrix, then it's equivalent to say that that matrix is orthogonal. To say that for any x, for any vector x, if I compute the norm of the vector qx, it's the same as the norm of the vector x. And if I compute the dot product of the vector qx and a vector qy for any vector x and y, I get that this dot product is equal to the dot product of the original vectors x and y. The one that's really, really important is this one. So what does that say? So remember, you have seen this in first year. I did not emphasize this very much in the review, but a matrix is a way to represent a transformation of space. So when you apply a matrix, you apply a linear transformation of space, which you've looked at properties of in most of the courses. Can't remember if you do that in 1210, but you see what I mean. So that property number 2 here, what it says is that if you apply that transformation that is encoded, if you want, by this matrix to any vector, you get a vector that has the same length. Okay, so that's why we call it an isometry. It does not change the length of vectors. If I apply Q to any vector in space, it's going to change it in terms of the orientation, or it's going to do things to it. But whatever it does, the result is going to be a vector that has the same size as my original vector. That's a very interesting property to have, okay? Because it means we're transforming space, but we're not transforming distances. We're changing things around without changing their lengths, which is good. And given these properties, we can then look at more properties. And so let me enumerate those. Okay, so if I have an orthogonal matrix, then the rows of the matrix are also an orthogonal set. So remember that we're looking, the definition of the orthogonal matrix is that I have column vectors that form an orthogonal set. But if I do have an orthogonal matrix, then the row of the matrix also form an orthonormal set. Okay, and that's quite easy to show. All these properties are easy to show. I'm actually going to show you one of them, but all of them are quite easy to show. Theorem 10 is one of those nice illustrative theorems, I think. So from our remark here about orthogonality, you can see that quite simply, if I have a matrix that's orthogonal, then its inverse is also going to be orthogonal. And that's also very easy to see. Number 3 is actually one, if you're curious on the mathematical side, I recommend that you give it a shot. This one is maybe a little difficult. It's probably the hardest of all of those properties, but it's actually quite cool. So if you have an orthogonal matrix, you can be assured that the determinant has one of two possible values. It's either +1 or -1. So orthogonal matrices have determinants +/-1. Number 4, I'm actually going to show you because it's eigenvalues and eigenvectors are very important in this course, and so I think it's everything that touches to eigenvalues, eigenvectors is worth mentioning. And so for any lambda in sigma of q, so I'll remind you, and every time I will, that I'm denoting sigma of q versus what we call the spectrum of the matrix, that is the set of all its eigenvalues. So what that statement number 4 says is that for all eigenvalues of the matrix Q, the modulus of lambda, lambda being an eigenvalue, is equal to 1. Okay, that's also quite striking. It's a bit like the property for a determinant. Okay, these are matrices. You can think of them as having a lot of properties, but whatever eigenvalue you pull out of that is going to have a modulus equal to 1. And also, if I have another orthogonal matrix and of the proper size to be able to multiply, so orthogonal matrix means it's square, so my second matrix Q2 must be also in Mn. So suppose I have an orthogonal matrix. The product of two orthogonal matrices is an orthogonal matrix again. Okay. So as I said, let's prove number 4 in theorem 10. And you'll see it's very, very simple, but I'm sort of emphasizing it because I want you to understand the mechanics. So let's take a matrix Q that's orthogonal, and let's take an eigenvalue lambda of this orthogonal matrix. So if lambda is an eigenvalue, this means that there exists a vector x that is non-zero. I remind you that this is super important. The vector x is non-zero if it's an eigenvector. So lambda is an eigenvalue if there is a corresponding eigenvector x non-zero such that q times x is equal to lambda times x. This is the definition of an eigenvector eigenvalue pair. Now let me take the norm on both sides. I'm completely allowed to do this, okay? This is I have an equality. I can do whatever I want to my equality, essentially, provided I use the same function or the same operation on both sides. So if I take the norm on both sides, I get this equality here. Okay, norm of qx is equal to norm of lambda x. These are both vectors, okay? And I'm taking their norm, so that's their length, and considering this. Now, from that theorem just before, that all conditions are equivalent, if I have an orthogonal matrix, then I know that the norm of qx is equal to the norm of x. So I'll use this here. From that theorem, I know that qx in this equation is actually equal to x. And from the properties of norm, I know that the norm of a scalar times a vector is equal to the absolute value or modulus of that scalar times the norm of the vector. Okay, so that means that the right-hand side lambda x, norm of lambda x, I can write as this product here. So if I take this equation again and I replace the left-hand side by what I just found and the right-hand side by what I just found, I find that qx is equal to norm of qx is not equal to norm of x, and the right hand side is that norm of lambda x is equal to modulus of lambda times norm of x. So when I have this equation, I can, so these are scalars, okay? So norm of x is a non-negative real number. Modulus of lambda is a non-negative real number. And so I can divide both sides by x, because remember that, as I stress every time, what's really important is if x is an eigenvector, then it's non-zero. So its norm is positive. So I can divide both sides of this equation by norm of x, and I find that the modulus of lambda is equal to 1. Okay? Okay, so before we finish, before we get into the meat of the problem, let me go back to projections, because we're going to be using projections. So we actually talked about them in the past, and I had given the definition of the orthogonal projection, I believe, but I had not given the component of a projection. So let's go over these definitions quickly. So the first one, 11, is, let me take a subspace and an orthogonal basis of that subspace. It doesn't have to be orthonormal. If it were orthonormal, actually things would be easier, because that norm of u1 squared and norm of uk squared that you see here, they would all be 1. Okay, but if it's not an orthogonal orthonormal basis, if it's just orthogonal, you end up dividing by these things. Okay, so take a basis u1 to uk of that subspace W, then we call orthogonal projection of a vector v in Rn. So the vector that you're projecting is in the overall big space, whereas the space onto which you're projecting is a subspace. So again, the simplest example to bear in mind is, suppose I'm looking at R3, I have my points in R3, and I'm considering what happens if I project on the XY plane, for instance. Okay, so that would be, the XY plane is a subspace of R3. It's a two-dimensional subspace, and I can project my points down onto this XY plane. This is exactly what we're doing here. So the orthogonal projection of the vector v onto the subspace W is given by this formula, which is quite simple, if you look at it. So it's the projection onto W of V, and it's given by the dot product of U1 times the vector that you're projecting, V, okay, dot U1V, divided by U1 dot U1, or norm of U1 squared, times U1, plus, and so on and so forth, until dot product of UK times V divided by norm of UK squared, so UK dot UK, times the vector UK. And you can see in passing that this involves the vectors U1 to UK, okay? And these vectors, they're in W. They're not in the original big space. They're in the subspace. So if you're projecting onto the XY plane, you're using vectors, for example, in free space, and you're projecting on XY plane, you're using the vectors in the XY plane to project. And the component of a vector orthogonal to a subspace is now another vector, and this time you'll see, I mean, it's the same idea, but here I have V, which is in the original space. Okay, so the component orthogonal to a subspace is, if you think about, I have a vector, I project it down onto my XY plane, that little piece that takes me from the tip of the vector to the xy plane, for example, that's the component orthogonal to the xy plane. Okay, and you compute it by taking the difference between the vector that you're projecting and its projection onto the subspace. Okay, so this is just to explain, and I thought it was worth spending a little time on this because it came up before and I hadn't really detailed, so I might as well do it now. Now, I'm not going to spend so much time on this. The purpose of what I'm going to show you now, the philosophy of what we're trying to do, is that, okay, I can have a basis for any subspace, but it actually is very useful when I have an orthogonal or an orthonormal basis for whatever object I'm considering. Okay, because orthogonal bases have nice properties, so it's important to be able to do that. So to compute this, we're going to use something that's called the Gramschmidt orthogonalization process, or the Gramschmidt process for short. And that process, what it does is it takes a basis, an existing basis of some subspace W, and it transforms it into an orthogonal basis of that subspace, that same subspace. So it's a process that takes something that exists and makes it into something a little better. That is an orthogonal basis instead of just being a basis. So let me and here, this is something where I will work through an example by hand. Okay, I'm going to show you the theorem, but for the moment, don't pay too much attention to it. When we look at an example or two, it will make much more sense. So the Gramschmidt process consists in doing the following. So let me take a subspace. I said subset, it's subspace. I need to mark a few things here. And let me take a basis, x1 to xk, of this subspace. So recall, at the risk of repeating myself, but I think it's important, recall that this means that x1 to xk spans W and is linearly independent. But there's no assumption on orthogonality. To get to apply the Gramschmidt process, what you do is the following. You define a vector v1 that you take to be your first basis vector x1. Okay. Then you define a vector v2 that you define as being x2 minus this. Okay, which is what? So if you go back to the definition of the projection, this would be the projection onto the subspace W1 that you just created. Okay, so my first subspace is the one that's spanned by V1 or by X1. My second subspace is the one that's spanned by x1 and x2. So remember, x are the original basis vectors. So second step, I take x2 and I subtract from it that projection. Then third step, I take x3 and I subtract this projection here. Okay, and I continue until xk, and to xk I substitute vk, which is defined this way. Okay, we can also define the subspaces of a subspace. Essentially, W1 is the subspace that's spanned by the first of your basis vectors. The W2 is the space that is spanned by the first two, and so on and so forth until you get to all the vectors in the basis. Then what we have is that for any number of vectors that you take in that list of vectors v1 to vk, you have that v1 to vi, so I here is a number between 1 and k, that set is an orthogonal basis for the corresponding wi. And in particular, if I take I equals to k, so that means the entire subspace, then that set v1 to vk is an orthogonal basis for w. So I've started with something that was a basis, but I wasn't entirely sure what it was, and I've transformed it into a basis that is now orthogonal. Okay? So that's a very interesting process. And this is a process we'll have to use to compute the so-called QR factorization, which is what we get to here. Now, QR factorization concerns matrices, but remember that matrices are just a good place to store vectors. Okay, so let me take a n by n matrix with linearly independent columns. Then I can factor that matrix whenever, okay, whatever the shape of the matrix, I mean, provided the columns are linearly independent, I can factor the matrix as the product of two matrices, where one of the matrices has the same size as the original matrix, okay, it's also n by n, and it has orthonormal columns. Okay. And the second matrix, R, is now a square matrix that has as many rows and columns as the original matrix A has columns. And that matrix has the property that it's non-singular, which I'll remind you means exactly the same thing as it is invertible. Okay, it's non-singular and it's upper triangular. Okay, so I can take any non-square matrix A, and I can show, and we're not going to do it, but it is possible to show that any matrix like this can be written as the product of an orthonormal matrix, an orthogonal matrix with orthonormal columns. So it goes even further. Its columns are not only orthogonal, they're orthonormal. So the product of a matrix like this and an upper triangular non-singular matrix. Okay. So what's the point of all this? Well, the point is that if I go back to least squares, the theorem that we had before in terms of existence of a solution, well, we can reformulate it this way. So let me take a matrix A in Mn of size Mn and assume that it has linearly independent columns. So if you recall, this means that the solutions to the least squares problem is a solution and it's unique. So if I take a QR factorization of the matrix A, which I know to exist, okay, from the argument from this theorem here, I know that my matrix A, if it's linearly independent columns, then I have a QR factorization. So if I write A as QR, then the unique least square solution x tilde of my least squares problem ax equals b is given by x tilde is equal to the inverse of R times the transpose of Q times B. Okay, so I have to take this last proof again because I always forget that I have to throw in an empty slide as my last slide, otherwise you don't see the whole slide. I don't know why the program does this, but never mind. So let me show you the proof of theorem 15, which is this theorem we just saw. And let me stress that one of the reasons why I'm showing you this proof is that it's very, very simple. Okay, and I think it's also quite illustrative of the way the computations can be performed in matrix analysis. Okay. So we want to show that the solution of our least squares problem takes the form that is announced in this theorem. Okay, so x tilde is equal to R inverse times Q transpose times B. So we start with the assumption that A has linearly independent columns. And from this assumption, we deduce two things from results we've seen already. The first one, which was in the previous set of slides, is that the least squares problem, AX equals B, has the unique solution x tilde equals to A transpose A inverse times A transpose times B. And the other one is from the theorem we just saw a couple of slides ago, which is that the QR, because the columns of A are linearly independent, the QR decomposition exists, or it's another name, QR factorization, but we also call it a QR decomposition. So the QR factorization exists and gives you a matrix Q that has orthonormal columns and a matrix R that is non-singular, that means invertible, and upper triangular. Okay, so what we do is we go back to the normal equations, okay, and I'll remind you that the normal equations are these equations. A transpose A times x tilde is equal to A transpose B. And what we're going to do is we'll start by replacing A by what the QR decomposition actually gives us. So we know that we can write A as QR. So every time I see A, I'm going to replace it by QR. So I have an A transpose here. I replace it by QR, and then I transpose. I have an A here. I replace it by QR. I have an A transpose here. I replace it by QR to transpose. And now I use the fact that when I take the transpose of a product, it's equal to the product of the transposes with the order flipped. So this first term here is RT times QT. I still have my QR here, so this is QR. And here again, this is RT times QT. Okay, nothing fancy so far. Here you can see we have QT times Q. And recall that one of the conclusions from the QR factorization theorem is that Q has orthonormal columns. And I'll remind you of a result we saw a while back, which was that it was necessary and sufficient to have an orthogonal matrix that, where am I? Sorry, where am I? Yes, that's the one. Here. Okay, sorry, I'm getting the theorem wrong. But if we have an orthonormal set in the columns of Q, then the product of Q times Q transpose times Q was identity. Okay, remember this was this argument that we are trying to show that the dot products are zero unless it's the same entry, that the same vector that's being multiplied by itself. Okay, so when I see, oops, now I'm on the empty slide. When I see QT times Q here, because the columns of Q are an orthonormal set, this means that QT times Q is equal to identity. Okay, and in terms of size, QT is Mn, QT transpose is Nm, so QT transpose times Q is Nn. So the identity we pull out here is of size n. Multiply anything by identity, you still have anything. So identity disappears here, and we get R transpose times R here, and here this hasn't changed. It's still RT times QT. Now, if a matrix is invertible, its transpose is also invertible. This is I don't remember if I put it in the review slides, but this is a very classic first year result, which you probably have proved. So when I see a transpose, an expression like this on both sides, I want to make it disappear. Okay, I've got an RT here and RT there. Well, how do I make it disappear? Well, I just hit it on the left with the transpose. So I multiply on the left by RT transpose both sides of the equation, and that gives me, so RT transpose inverse times RT. Oops, I forgot my RT here. Okay, another thing to fix. RT transpose here times RT and RT transpose times RT, they both give you identity, and so they disappear, and so you're left with R times X tilde equals QT times B. And the same way as we just did, we want to get rid of this R here, so we multiply both sides by R inverse on the left, and so finally we get X tilde equals to R inverse QT times B, which is the result we wanted to prove.